Okay, in this item we're asked to find the deflected shape of the beam and to justify that shape perhaps by looking at the actual moment diagram and discussing how that's all related, and then define the vertical displacement at point E right here using appropriate technique. So let's check out what this system really looks like. At A we have a fixed end, so we've got 3 reactions there. We have 2 internal hinges, we have a roller at F, and we got a roller at G. So there are a total of 5 reaction components. We have 3 equilibrium equations, so equilibrium conditions, plus we know that the moment at C internally and the moment at E internally are 0. So we have 2 special conditions. That gives us 5 conditions of equilibrium, and that means that we are statically determinate. So we don't have to make a guess about the moment diagram. We can go right at it by just going and finding the reactions and drawing the shear diagram and the moment diagram. So let's start with the middle part, this little sort of like a suspended piece or simply supported piece here from C to E. We've got the 6 kilonewton load that acts right at the middle, so the shears on the 2 ends will have to be 3 and 3. That's a pretty easy one to figure out. Immediately transfer those down as shears. There's 3 and 3, and then because we're to the right of the hinge, now the 2 kilonewton load shows up then on this left free body diagram. It's a common mistake to make, is to put that either in both or not put it in at all. And notice that now we have enough information to be able to get things such as the vertical reaction over here at A. It's a simple sum of those, so that's 11 kilonewtons total, and then we got to get our moment. Well, we will have to do a little math there. There's 5 times 4 plus the 6 times 2, or 32 in a frowny face manner for the kilonewton meter, and the moment there at the left end. And then we come over here, we might anticipate that we're going to have a vertical reaction up at F and a vertical reaction up at G. It just kind of depends a little bit on how big of an effect this 3 kilonewton shear is at E that wants to, this load is coming down here. It's trying to push down point E, dragging that down. Okay, that makes sense here. And so we've got our reaction at 2 locations. There's your GY, there's your F sub Y. If we sum moments about point G, then we would get 3 times this whole moment arm. That's 3 times 8, plus then we get 2 kilonewton per meter times 6, so that's 12. So plus 12 times that moment arm is 6. That's 96, and divide by 6, and we get 16. I don't think that's right. I think I might have done something wrong there. 3 times 8 plus 2 times 6 times 3, not 6. I got the moment arm wrong there. That's 60, divide by then the 6, and we get a 10. Now, how did I know that that was probably not the right number? Because I had 3 plus a total of 12, so that's 15, and this reaction's way out here, and I came up with 16. That just seemed too big. And so now we'll sum moments about F. We're not going to sum forces in the Y here, because that would just probably double count the mistakes. 2 times 6 times 3 there, and then minus 3 times 2, that gives us 30 divided by the 6 meters. That's the 5 that we get. That's 15. That balances out the 15 that comes from the load. Okay, so now we can go get the shear diagram. Hey, this should feel very comfortable. We've done this many times in the past 3 years. Go up to 11, go over constant, back to 11, drop down to 5 as a net, go constant for another 2 meters at 5, drop down by 2. I don't know if you're paying attention here, but I'm using millimeters as my scale. That's a net of, let's see, I went over 11, down 6, came over, and we're at 2. Wait a minute, how does this work? I go down by 2, so that's at 3. Oh, that matches the positive shear that I showed there. right? And then we come over flat, and we're at 3 and drop down by 6 to a net of a negative 3, which is of course what we also had for the shear there. So that seems pretty good, and that's going to be constant all the way over to the reaction, and then it'll go up by a net of, or not a net, but go up by 10 to a net of 7, and then we're going to have a linear drop off down to 5, and so then we close off by the 5 there, so that's good. Right, so 5 divided by 12 times our 6 means that that's 2.5 meters, and that would leave us a net of 3.5 meters over there. We'll need to know that when we go get the moment diagram. Right, so this is maybe not how I anticipated started doing this problem, but hey, you know, it's what it takes. So now we come down here, minus 32, frowny face, right? So frowny face there, that's what the negative, or the arrow there, that's the kind of bending that's going on, that's a negative. And then we'll go up by this area, that's 11 times 2, so 22 plus 22, so to a net of about plus 10, not about, it is plus 10. Or sorry, it's a net of negative 10. And then we go 5 times 2, that's 10. Oh, we get 0 right at the hinge. That's exactly what it was supposed to be. So that makes me feel very good about how that all played out. And then we got 3 times 1 over to point D. So it changes slope a little bit. And then we have another, then negative 3 times 1 meter there, 1 meter there, to get back to 0. Happy about that, but we keep the same slope. And that will be 3 times 2, so a negative 6 looks to be where our moment is right there. So that was positive 3 at D. There's point E, there's point F. And then let's see, we've got 3.5 times 7 divided by 2 for a net of 12.25 positive minus the 6 that we started at, and so we end up at a plus 6.25, and then we're going to subtract off 2.5 times 5 divided by 2. Hey, we get back to 0 just like we're supposed to, and that's a second order curve. Feeling very happy and positive about how this is all working out. And then let's just get this finished off. We know that positive bending moment means positive curvature, so that's positive here. That means positive curvature. That means we're going to have a deflected shape that goes up like that. We have, and notice the symmetry that we're going to end up with here. 2.5 over here will be balanced by over 2.5 to here, so the inflection point is a net of 1 meters from there. Right, and so this is, of course, negative moment, so therefore negative curvature, so that's going to curve like that. Then we got the little simply supported segment in the middle, that's positive curvature, so that'll be going up. And then everywhere from C to the left is going to be, of course, negative moment, so negative curvature or curvature downwards. So that means the deflected shape should then be something along the lines of follows. Here's our fixed end over at the far left. We're going to draw our delta in. We got a hinge at C, hinge at E, no displacement at F, and no displacement at G. And through this whole segment of ABC, we've got downwards or frowny face deflected shape. So let's get that in. And bam, all the way to the hinge and then stop. And then we've got what's going on over here. We've got a smiley face for most of this segment here and a little bit of frowny face, which makes me think that there's a whole lot more smiley face than there is frowny face here. So I think what's going to probably happen when we get done calculating things is that the middle portion between F and G is going to dominate over what happens with a little bit of frowny face curvature or hogging curvature. And so I'm going to lay this out assuming that point E is probably going to have a net writing up rather than down, but who knows? We want to have zero displacement there, so we've got to be careful how we zero displacement at F. That looks a little chunky there. It needs to be smooth as we go through there. That's point F. There's point E. It has gone up a little bit, and then we have a little smiley. At least I'm guessing that it has. And then we have a little smiley face that goes in between. This is grossly exaggerated, without any doubt. And we'll show our extended tangents to indicate that we have a break in the slope of the beam. Boom. All right. So that's not, terrific, but it's not bad. And now we're asked to go find the displacement delta E. Whew. Wow, this is getting long, huh? All right, so that's what we're now wanting to find. Now we could do moment area method if we wanted to. I don't particularly choose to here, but I'm going to use some of the concepts from moment area method. And so some of those concepts are thinking about how this displacement that I'm seeking here could be thought of in a couple of ways. If I only knew the rotation at F, I could figure out what this extension is here, and then the tangential deviation would give it to me. I could find that rotation over here. Now this gets a little complicated, so what I'm going to do is actually do this in two stages. All right, notice I'm working with that simply supported piece off to the side, and because it's just easier to work with. And I might as well work with the piece that first finding the effect from the distributed load, because the moment diagram is a lot easier to work with here, and this is going to be one of the cases that's in somewhere in a beam table, if I can find those beam tables, doggone it. And then we'll add to it the effect that comes from the diving board, which is going to be this shear of 3 out here. Why not do it that way? And so actually works out pretty convenient to do it that way. You could do it all at once if you so choose. I choose not. And so we'll see how this all plays out here. It's a little complicated, I guess. Not really. We've got the smiley face there. Now note this cantilever here is going out for the free ride. So all I need here is theta F. We're going to call that prime. That's the only part I need here to get to the little piece delta E. We'll call that prime. All right, so we're after the summation of both of these, and this is going to come from an interesting little piece here that we'll play with. We'll see what we've got going on here, but we want this whole piece down. That's going to be our delta double prime E. And we'll see how all this plays out here in just a second. Let's get our beam tables out available to us and see what we've got. We've got cantilever segments. That might be useful later, but let's start with a distributed load on a simply supported beam, and it's a uniformly distributed load. That makes it easier. Aha! Voila! There we go. There's our distributed load, uniform over the whole length, and our rotation at either end is the W times L cubed over 24 EI. So theta F prime is W L cubed over 24 EI. Okay. And L in this case would be 6 meters. So that's 2 kilonewtons per meter times 6 meters cubed. We aren't given EI, so we'll have to have an answer that's only in terms of EI. And what's that going to be? 2 times 6 times 36 divided by 24 is 18 EI. Oh, 18 what? Kilonewton meter squared over EI. And delta prime E then will be this distance, which was 2 meters times theta prime F, so that's going to be 36 kilonewton meter cubed over EI. That's how much that part goes up. Now, how are we going to find this little part? Well, a little tiny portion of this is just the cantilever beam portion, right? And then the rest of this is a simply supported beam that has a moment that's applied to it. Not sure if we've got one of those. Oh, hey, we do. Look at that. We've got a simply supported beam that has a rotation. When the moment's applied here at A, that's ML over 3EI. So what we're going to do is we're going to go find out what that rotation is. Theta, that's F, or that's going to be double prime. And so theta double prime F is equal to that M naught times L over 3EI. Now the L we're talking about here is the cantilever. Oh, no, it's not either. Oh, we got to be careful here. That's the 6 meters here. So that's 6 meters. The moment comes from this 3 kilonewtons times 2 meters. So that's 6 kilonewton meters over the 3EI. I think I might be able to do that one in my head. 6 times 6 is 36. Divided by 3 is 12 kilonewton meters squared over EI. Oops, sorry. Kind of tilted the paper there on you. All right, so that's just this little portion, well, the beginnings of that little portion. We then have to take that times 2. And so that would be 24 kilonewton meters squared over EI going downwards. Right? And then we need the little tangential deviation, which just comes from the cantilever beam and a load out at the tip. I happen to know that one right off the top of my head, but I'll show you where we're going to get it. There you go. There's your PL cubed over 3EI that we get there. So that little tangential deviation, again, we'll call it double prime. E with respect to F is going to be the magnitude of that tip load times that length cubed over 3EI. 3's cancel out. 2 cubed, that'd be 8 kilonewton meter cubed over EI. So that's interesting here then. Our final delta E is going to be the sum of our delta prime E plus our delta double prime E. That's this piece right here. And that's going to be given to us by, we have 36 kilonewton meter cubed over EI. That was going up, and then the other is going down, and that's going to be the sum of the 12. Nope, it's not either. Let's see here. It's going to be the sum of these two, and so that's our 32 kilonewton meter cubed over EI for a net of 4 kilonewton meter cubed over EI, and that would be going up, and that's our answer there. So when you work it out slowly, it does take a lot of time to piece it all apart. Well, there you go.